Okay, we're going to be back with building a joypad thing for Sega Master System, but starting at the very beginning. So I needed to have this is the recap from the previous video, I needed to have a 74HC157, which I didn't have. I do actually have them now, they've arrived in the mail. But we're going to continue with this. And so last time we went through this process and made a board which looked a bit like this, but I've taken most of it apart. Try and build what are they actually called? I've forgotten what they're called. But basically you can select between, so you have 4 inputs, you have 2 sets of 4 inputs, 1 set of 4 outputs. By changing what is on the value of select, you can choose which of the inputs appear on the outputs. That's what the IC does. So I wanted to make one out of other ICs, and so the last time we did this, that was like my little truth table of how it's supposed to work. So if you're on input A, you have 0 and you have select that, then you should get what input A is on the outside. And we went through and we came up with this sort of diagram, which was how to get that using an OR gate and 2 AND gates. So basically if the select and B, then the output will be 1, will be high. So basically if this is 1 and B is 1, the output will be high, and if B is 0, the output will be low. And the inverse is here. I'm not going to go too much into this because that was the whole video from the previous one. But that was the refresher. I just have to find, I think I've got my pages in the wrong order. Hopefully you didn't see that little bit there because I'm giving it away. But the idea was, let's create this from a Nand gate. And I don't have a picture of a Nand gate. Well, I do have a picture of a Nand gate, but it's going to give the answer away. Don't ruin the fun. So we're going to cover that part up there. So the Nand gate looked like that. It's just an AND gate, but it has an inverted thing at the end. So if both of the inputs are high, the output is low, and if either of the inputs are low, the output is high. So basically it's like an AND, but you negate the output, or you invert the output. So the question is, that's a very common IC, and it's more common than OR gates and AND gates. And it's useful because it's called a universal gate, because you can make other gates out of it. So I thought I'd go through and we'll see if we can make what we were making before, but we're just going to use NAND gates basically. So sorry for the terrible handwriting, but in this case here I'm using my left hand because my right arm is still not better, but it is getting better. Like the last few days it was getting worse, and today it actually genuinely seems to be improving. I've decided to build. I've got my little thing here now. I should probably show this because it's electronic channel. Can't really get it all the way over there because the cable is not working. Hold on. I can unplug it. It's currently still plugged in. Sorry, things are a bit of a mess. So this is my little prototype. I haven't actually finished soldering it up, but basically it's just a little joystick controller thing that you can use in place of the middle mouse button. But I thought I'd put more buttons on this. But I thought actually a better idea, I've looked into these things, is this is just using a Arduino micro clone, to also have foot pedals to do the mouse buttons. So I think I might try and do that, but we'll get some sort of foot pedal thing to do the mouse buttons. So basically I just kind of want to get rid of all mouse usage altogether. If possible. But anyway, we're here to do gates. So how to make an AND gate from a NAND gate. Now that's the really easy one, right? Because you can make an inverter. So this part here is just how you make an inverter. So if you tie the inputs together, then if the input here is high, then both the inputs into the NAND gate will be high and the output will be low. And if this input is low, then both the inputs will be low and the output will be high. So that's it. That's basically an inverter. So this is just taking the NAND gate, which has an inverted output from an AND gate, and then inverting it again to get back to what an AND gate would get. So it's really easy to make an AND gate out of that. But it's not so easy to make So I'm just going to bring that back here. So basically what we're trying to do is we're trying to make, out of NAND gates, these gates here. So we don't want to use any OR gates or AND gates. But we can build, I just showed you how to build AND gate using 2 NAND gates. So we can get 2 NAND gates here and 2 NAND gates here. Don't worry if you're watching this getting frustrated that there's an easy way of doing this. We're going to get to it. So now we have to work out how to make an OR gate. Where did I put my little page? I did not actually organize this as well as I was hoping I was going to. And so we're going to get to what this thing here is in a second. So creating an OR gate from a NAND gate. This one was kind of complicated. So basically you're inverting the input. So if you think about it, if both of these are high, the output is low. But the output is high when either of these are low. So this is the way to think about it. The output becomes high when either of the inputs are low, because the output is only low when both of the inputs are high. So if either of them are low or both of them are low, the output will be high. And this kind of feels like an OR. So OR is either or of these things or both of them. And so all we're doing is we're saying, well, we're going to invert the inputs. This kind of looks like some funny little mushroom or something. But we're inverting the inputs. So if this input was high, this will be low. And if this input was high, this will be low. And the result of this, of course, is just going to be an OR gate. So if this input was high, that will be low. This then will be high. If this was high, this will be low. And then that will be high. And if they're both high, then they'll both be low, and then it will still be high. But if both of them are low, right, so both of these are not true, or these are false, if we're talking in Boolean terms, then both of these will be high, and that will make a NAND gate go, oh, okay, it's there. Both of these, this and this are high, so the output will be low. So that gives you basically what you would think an OR gate does. So if both of them are low, both of them are high here, and the output is low. And that's the only way you get the low output, which matches up with an OR. An OR is only low when both the inputs are low. And that will happen here as long as you go through these 2 inverters. So that's the way of creating an OR gate. And I just sort of wanted to quickly talk about because that's basically I think it's a De Morgan's rule. So if you ever do any sort of Boolean logic stuff, then this kind of comes up. But it's sort of an interesting way of for me, I don't know, I always think of this rule, and it helps me remember how to switch around between 2 different types of things. But basically, if you have an AND thing, so this is 2 ways of writing Boolean logic. I probably should have gone for the 3rd way, which was the full computer sciencey way, which is instead of using a tilde for a not or an invert, I should have used an exclamation mark. So I've really kind of gone all over the show. It should be an exclamation mark here. But this little triangle this way is and the triangle the other way is or. But you could also use a vertical line or an ampersand. I kind of was sticking with this way of writing things because I find it really hard to write ampersands in general, and I find it very hard to do it with my left hand. It will be the last thing I get good at. But basically the rule goes, if you invert the whole expression, so this is in brackets and you're inverting it, so brackets inverting the whole result of the internal bit, this is equivalent to inverting the internal bits separately and flipping around what you're doing. So if you're going A and B inverted, or not A and B, it's the same as, you shouldn't say it not A and B, so it's not the result of A and B, is equivalent to not of A specifically, individually, and not of B, but ORed. So I don't know if I'm explaining it very well, but A and B knotted is equal to not A or not B, and conversely, so these 2 things here are the same. I've just written them in 2 different ways. Conversely, the other way of saying it is A or B inverted or knotted is equivalent to A knotted and B knotted. So this is how you can convert between an AND gate and an OR gate, or an OR gate and an AND gate. And of course, these things here are both the NAND and the NOR. So this is a NOR gate and a NAND gate. And so these are very common in electronics. These are the universal, I think there's another one, universal gates, so that you can create other things out of it. And I just find that because they match up with this, and so if you've ever heard this term, that's kind of what it's all about. So I just thought I'd mention that. But I'm going to quickly go back. So this is the diagram. So I've just gone through how to make an AND gate out of NANDs, and how to make an OR gate out of NANDs, and also how to make the inverter out of a NAND gate. So this is one NAND gate with the inputs tied together. And so you would get a basic idea of how to convert this whole logic diagram into a NAND gate one. Would look something like this. So I hope this sort of comes across as how it's making some kind of sense. But here's the inverter here. So I've done my inverting part. And then we've got our first AND gate, which is the AND gate with the output inverted. So there's my A and my S. So that kind of matches up to this picture here. So that's that bit there. And so on for this one, B and S and B. So this is S is select in this case. So we have to invert the select here, but we don't invert it for the B. So same kind of thing. And then we've got a complicated little OR gate over here where we've got an NAND gate and we've inverted the inputs. So that looks like well, that's a lot of work. There's a lot of extra gates there. That looks we've got 1, 2, 3, 4, 5, 6, 7, 8 NAND gates. And here we've only got 1, 2, 3, 4 gates used, and this gate is shared across all of them. And so you've got 3 times 4 because you've got 4 inputs plus 1. And so in this case here you've got 7 times 4 plus 1, so 29 versus 13. Looks pretty bad. But we can actually look really closely at this, and you might notice a few things. First off, we've got 2 inverters in a row, and that's because we're taking the output of our AND gate and then we're inverting it, and then we're passing it on. But this thing here needs its input inverted to do this. So because we're inverting twice, if you take something that's high and invert it to low, and then invert it, you'll get back to high. And if you're low, and then you invert to high, and then you'll invert it again back to low. So there's two inverters in a row is pointless. There's no point doing this in general. Maybe there's some buffering thing you might want to do, but in general, this is not something you'd ever do. So you can actually just chop that out. So you can chop that bit out, and the same as this, you can chop this bit out. And so then you actually end up with a simplified version, which looks like that. And this is quite neat. I think it's quite neat, because it actually looks pretty much the same form as the original one. So you've got, here's your output, here's your things, your input things, your A and B and your select, and that's the same kind of little tree-like structure that you get on this, on the original one. So this one makes a lot of sense. Intuitively, this one you have to sort of work for, but the nice thing about it is you end up without having to need any extra gates. This kind of works all the same. This is shared across everything. You just have to use one extra NAND gate, and so you could do the whole thing just with NAND gates. Which is probably how they do it internally, because NAND gates are easy to make. And so I went ahead and I made one. So here I made a complicated little soldered up a little PCB thing, not a PCB. It's not a printed circuit board. It's just a prototype board thing with lots of little wires all over the place. It's all real crazy. I did actually mark some of the wires, so it's not completely bonkers. But these are basically 3 NAND gates, and they're kind of laid out the way this is. So this NAND gate here takes care of the 4 from one side. That takes the care of the NAND gates for 4 inputs on the other side. And this one in the middle is the linking NAND gate. So they're all linked to those 2 here. And this is kind of important for why I've done this, because I'm going to just quickly try something at the very end of this video. So it looks like that. So that's how it works. So if I turn it on, what I have got is I have got a little switch here so that I can switch between the 2 things. And what you can't see unless I lift the whole thing up is the little dip switches which are in the middle. And basically on this one here, I've got 2 down and 2 up, and these ones are down and these are up. There's kind of they're upside down for you, so those 2 are up. So if I actually move this, it will. They keep falling out of the breadboard. They're not really good at breadboard stuff. You can flick those around if it stays in the breadboard, which it won't. And you can flick these around and nothing happens. You're gonna have to trust me on this. Really don't work on breadboards. Those 2, nothing will happen if you do this. So right now though, this is too high and too low, and that one is what you can see on the LEDs. There's a little LED here which is for the inverted output. So when I flick to this, I'm going to switch to the other set. So if I do that little switch, you're actually over. So if I make it like this, so these are too high, too low, which is why you get the LED thing. This is now too low and too high. Sounds like a Fast and Furious movie. So if I flick between the 2, you get the 2 different outputs. So it does appear to work as it is supposed to, and maybe I'll make them all high on this one. Alright, so and then we'll go back, and that's only going to be too high, and that one's going to be all off. So now it's going to be on and off, 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 on and off. So there we go, that's that done. So the neat thing I thought, which might be kind of fun to do, is, but I'm going to have to, I don't know how well this is going to work. So I thought that was kind of interesting. So we will make a Mega Drive controller probably out of these, but we'll probably start with a real 74HC157 now that I've got them. But I'm going to turn this off for a second. The nice thing about, where did I put my book? So we're going to look at the Master IC book. Last time I used a 74HC14, which is actually a Schmidt trigger inverter, but for these purposes it's the same. So that's what we use for the inverter. So I am cheating here. This IC here is an inverter, just a 74HC14, and I'm using a pull down resistor, and that's inverting the output, which is going to one side of the select thing, and the other one is going to another inverter, so it's basically being buffered, and then it's going out here to the other side of the inputs to everything. So basically this thing here is just going and being sent to 4 different inputs, and that one's being sent to 4 different inputs, and I'm doing the actual inverting over here, which is kind of neat because you could do something more complicated over here and you can use whatever inverting techniques you want. Quickly, just to labor the point. So that's a quad input AND gate, and the NAND gate is, well, there's the OR gate, and that's a NOR gate. They're actually completely different. Oh no, no. I hope this isn't the case. I actually had all planned. Oh, it's gonna go bad, isn't it? It is. No, that's the quad 2 input NAND gate. Oh well, that's good. They're more intelligent. So those ones that made me worried. I'm going to quickly explain why. So I did not use. So I used the 7.4. So a new IC, which is the 7400. So this one here. But hopefully it has exactly the same layout as. That's the same layout. That's good. It's kind of the same. Yeah, that's the same layout. It's not printed the same. They're not very good at this book, are they? Should have used my other little CMOS book, which I've lost. So the layout is the same for the NAND gate and the AND gate. So hopefully the layout for the OR gate is also exactly the same as the NAND gate. So right now it's using NAND gates, but there's literally no reason why we can't just swap out these. Oh dear. I'm just going to hold on. Just went and dropped a drink on the floor, and now there's like a wet patch on the floor. That's okay. I'll finish the video because why not? So the idea was, if I was to actually take these NAND gates out and replace them with an AND gate, two AND gates and an OR gate, we'd actually get the same. Is this thing going to come out or not? I hope I don't break this. Alright, so we're going to do this. Please come out. Did I break this IC? No, I didn't. It came out fine. Alright, there we go. So that one there is the NAND. They're all NAND gates, I know that. So we can take this out, and hopefully the behavior will be exactly the same. We'll just do this without breaking anything. No, that didn't come out so well. This does not work as well on taking it out of these things as it does. Maybe I should just pull straight up. Maybe there's a trick to getting it just right. Come on. Am I actually getting it? I don't want to break. I did spend quite a long time soldering. More time than you would think. Okay, so there are my NAND gates. They're all got the little notch facing that way. So let's just get out these little ICs from the previous one. Alright, so this one here, let's hopefully make sure I get this one right. That's an AND gate. So the AND gate, this AND gate can go over there. And that one's gone in. So this must be the OR gate. Just double checking the lights. So that's the OR gate. So we'll put my OR gate in there. So we're going from completely different ICs. So we're going from an all 74HC157 world, which was all the rave once. And now we're going to go, need an extra, because I didn't actually use two AND gates. So now we're going to put, let's just double check the right one here. Alright, that's an AND gate as well. So there we go, we've done it. They're all going in. That went in without me having to squash the legs, so that's nice. They go in pretty well here. Alright, so they all look very different. Is it just my eyes? Alright, so now, hopefully, we've replaced those gates. And now we've got the same diagram as we originally had, with an OR gate in the middle and two little AND gates on the outside. Or turn it on. Hey, okay. Oh, I kind of ruined the suspense. So we'll just put this in, and we'll make two there, and two there. Well, actually, I'm going to make it an exciting pattern. Alright, so that one's going to go like that, and that one's going to go like this. So if this thing works, and that actually can stay in there, basically will be either that one on and that one on, or it'll be that one on and that one on. So they should be like alternating like that. You'll see what I mean. So let's just see if it works. It better work. Oh, it didn't quite work. Oh no, what's happened? It's this thing? No, that's not how it's supposed to work. Oh no, it didn't work. Or did it? Something's not going right. Well, that was supposed to work, wasn't it? Well, that was just unexciting. Why does it not work? I feel like it should. Oh. Oh no. Okay. Well, it was supposed to work. Now I'm going to have to think about this, and then I'm going to go, oh wait a moment, it's obvious why it doesn't work. Well, the first LED works, but the rest of them don't. I have them the right way around, don't I? Oh no, the wires are coming off. Oh no, what have I done? I've pulled the wires off in my haste. And I'm literally not going to have any idea how they go back on. Well, first off, I think that one goes in there. Why do they make it like this? I have to admit, I didn't really think this thing through when I was making it. Because it's not really I think, why did I spend all my time making this? I did do some soldering. Alright, so that one's going there. So where does this wire go? Well, there are two wires here that do not go where I can tell what they're supposed to go to. So those two have wires. Oh, right, well this wire here. Oh, I think I've got it. Okay, so that one can go there, and that one can go there. It still does not look right. really doesn't. Okay. Wow, that side's correct. This side, not so correct. So if I turn it back to there, well, that's actually correct. That's correct. Okay, now it's kind of working. So it should. Oh my gosh. Oh my gosh, those dip switches just hate breadboards. Alright, so now I think it should work. Oh no, now they're exactly the same. Alright, okay. Okay, so it was working just a second ago because the pattern was the same. This is terrible. Like, what a worst. Okay, this is my all-time worst video because you can't see what I'm doing. Alright, okay. Alternating time, and they're looking very faint, so I'm probably doing something wrong. There's probably some voltage issues there. So can you actually see that on a video? Look, it does alternate between the two. The dip switches do work. So after having to rewire everything, you can in fact replace that falls out. These switches don't stay in very well. You can in fact replace those ICs. So you can replace those 3 NAND gates with 1 OR gate and 2 AND gates. So I hope that was interesting. I thought it was a cool and sort of interesting way of looking at gates if you don't know much about Boolean logic and that kind of stuff. And digital logic. Maybe I should call it that, digital logic. So anyway, I'm probably we are going to come back. I'm going to use this little board to make an actual controller because I think it will be funny. And also because what else am I going to do with it? But we will go with the 74HC157 for the next video, which will be about actually building a Sega Mega Drive controller. So thanks for watching, and bye.